Welcome for today's colloquium by Giovanni Volpe, who is a professor at Göteborg University. So he will be talking today how can deep learning enhance microscopy. So Giovanni is a full professor at Göteborg University and the head of soft matter lab. His interests are mainly within soft matter and many branches related to that. So besides microscopy, he is also working on neural networks, including medical applications, developing software, for example, for medical research on brain connectivity, very interesting things. And he was telling me earlier today, also he is interested in optical tweezers and various structure formation of various kind of soft particles. And he is full, as I mentioned, he is full professor at Göteborg University, and he is a recent recipient of the Göran Gustafsson Prize from the Royal Swedish Academy of Science with a quotation for boundary breaking research focusing on microscopic particles with active functions. And so now the stage is yours, and thank you for coming and telling us about your research.
Hey, thank you very much. So, well, thank you very much for the invitation to give this presentation here. So,
maybe
sure.
I forgot to mention at 4:30 there will be a meeting with students at Cafe Planck. So students, please proceed to Cafe Planck after this talk.
Okay, well, thank you again. So again, thank you for the invitation. It's also nice to have the meeting with students afterwards. And yeah, what I will speak about is one aspect of my research, in particular the work we have done over the past few years in applying deep learning to microscopy. But as Igor already said, we do a lot of other work in my group. In particular, we work also with optical trapping, experimental work with optical trapping, with active matter, and also with neurosciences. In case anyone in the audience is interested in discussing that, I'm very happy to. Okay, so what I will try to do today is to try to, well, I don't need to convince anyone nowadays. A few years ago, I would have said that I would have tried to convince you that it's a good idea to use deep learning for microscopy. Nowadays, basically, there is no need to convince anyone that they should use deep learning with basically anything. But I would like to give an historical perspective to start with. And I guess many of you recognize this picture. So this is the manual, digital in the sense of fingers, tracking of Brownian motion that Perrin did more than 100 years ago. So basically what Perrin did was to take some microscopic particle, place them in a microscope, project their image on a screen and track them manually. And by doing this, he managed to basically show that Brownian motion exists. And this basically demonstrated that matter is granular. So, practice, he demonstrated that atoms exist. So, for this he got the Nobel Prize. Because 100 years ago, scientists like us would have not believed in atoms. Most people thought atoms were a nice mathematical trick, but not existing for real. They thought matter was a continuum. So Perrin basically demonstrated the existence of atoms with this experiment. So a very, very early example of quantitative microscopy. And obviously, over the years, people start doing this more in an automatized way. In the 50s, 1950s, people start using electronics combined with microscopes. And one of the first works in which electronics was coupled with a microscope was from essentially coal mining, which obviously you shouldn't do. But at the time, people were very into coal mining. And one of the problems we have when you try to mine coal from the underground is that coal will release microscopic particles in the air. And if you reach a certain abundance of these particles, they can self-ignite, causing an explosion. So the first example of a digital microscope was essentially a particle counter that was counting how many particles of coal were there in the air. Now, obviously, this is not something that is very in use nowadays, but similar ideas then went into biology, into biomedicine, in particular into flow cytometry. So if any of you has done a blood analysis, essentially this is done by using the nth iteration of this kind of technology, where some laser light gets scattered by the blood cells in order to automatically recognize what they are. Then, in the field of soft matter, people started in the late 90s to use, the late 90s, what happened is that personal computer became very available also to labs around the world. So, especially the group of Crocker and Greer at that time proposed the idea of analyzing with computer algorithms videos of colloidal particles in order to study their behavior. And this has been a very successful line of research because many people have worked on that. And the nice thing is that with colloidal particles you can essentially simulate atomic systems to a very good degree. And the difference with atomic system is that you can see them with optical microscopy and you can track their evolution on timescales that are milliseconds and not picoseconds. And the final revolution in quantitative microscopy came just decade ago, I would say, with the advent of deep learning. So one of the first examples where really people understood the importance of deep learning for microscopy was with the invention of the UNet, which is a kind of neural network that permits to segment cells in a way that was totally unexpected until then. And also in this, later, people start also doing, including my group, particle tracking using deep learning. And in this line of research, we have basically then released a lot of software tools and new algorithms to improve microscopy with AI. So this is where we fit in the timeline, just to give you an idea. So in the evolution of how people do quantitative microscopy. And deep learning is really a newcomer into this. So, for the rest of the talk, I will try to give you an overview of what could be interesting aspects of deep learning with microscopy. I will start in particular from first I will give a very worked out example just to make you understand all the details that go into developing an application where we combine microscopy with deep learning. So we start from a problem, we show how we can improve the solution of this problem with deep learning, and how we can verify that it's actually a good approach instead of other ones. And then I will go very briefly over a few other applications, also trying to give a perspective of where I think the field is going to move in the next years. And finally, I will make a bit of advertisement for the software tools that we have been developing over the past years. So let's start with this first example. This is really the first example that we, in my lab, did to where we, for the first time, combine microscopy with deep learning. So the problem is particle tracking. So this is something that anyone working with colloids probably or cells will need to do at some point. So typically what you do is to acquire a video of the particles. And after... Typically, the kind of analysis people do is just a thresholding. So you take this video, you threshold it, so it becomes white blobs against a black background. And for each one of these blobs, you can measure the centroid, basically the center of mass. And the interesting thing is this centroid will give you the position of this particle down to a fraction of a pixel. Now, just for scale, these particles are in the order of a few microns in diameter, so a pixel will be maybe 100 nanometers. This means that you can easily, with this technique, measure the position of a particle down to a few tenths of nanometers. So we can, this is standard. This is something that everyone does around the world all the time. Very important to keep in mind that there is a difference between diffraction limit and detection and positioning limit. They are two different things. And what you do with this? Well, what you can do, for example, is to reconstruct trajectories over time. And if you have these trajectories, then you have Brownian trajectories, and you can verify that the particles are moving with the Brownian motion and repeat digitally the experiment that Perrin did 100 years ago. So this is more or less what people do. What's the problem? The problem is that to do this kind of analysis, you need a perfect video to start from. And the problem is that sometimes you don't have a perfect video, and this is the kind of video we had like 6-7 years ago. Here what you see are colloidal particles, which are these circles, and these are 4-micron diameter silica spheres. And what we wanted to study here was the motion of these bacteria, the fluorescent moving objects, which are Bacillus subtilis bacteria. And we wanted to see how they moved in this crowded environment, a problem in active matter. Because essentially what we wanted to understand is whether they would create some channels that then other bacteria could reuse. But to do that, we need to basically we need to measure where the particles are, right? And the problem is that this doesn't work with the standard method that I explained before because of a lot of problems. You see that there is a gradient. You see that there is a lot of noise. You see that you have a non-perfectly uniform illumination. Now, of course, I guess, I don't know how many of you are experimentalists, but you might be thinking, why don't you acquire better data? That's an obvious question. Well, because sometimes you cannot really acquire better data for many reasons. In this case, the problem is that we wanted a very large field of view because we need to do statistical physics, and we want to keep the illumination light to a minimum because the bacteria get photobleached. So if you want to acquire trajectory over a large area with as little amount of light as possible, you end up having something where you reach very close to the limit of the noise of your camera. So it's a kind of trade-off. But anyway, we had this problem. We wanted to analyze this video. And if you zoom in an area of the video, you see how complicated it is to analyze it. And the best you could do with the standard algorithm is this. So this was work done by a PhD student of mine that had been analyzing videos of colloidal particles for many years. So he knew what he was doing, and this is really the best he could get. And the worst part is that with standard algorithms, you get this quality of the result on this patch, but this works only for this patch of the video. It will not work for the other parts of the video. It will not work for a different video. So it's just not viable. And this is the point in which, this was maybe 2018, and there were basically people starting to think about deep learning in microscopy, and we thought we should try to use deep learning to solve this problem. And that's what we decided to do. And what we decided to do was to use a convolutional neural network. So you see this is a neural network that takes as input an image of a particle and has some convolutional layers that make convolutions over the particle. It gets an output that is a dense neural network, and the final output is the position of the particle, x and y. Okay? Now, I guess some of you are thinking about that. If we want to use this neural network, we need to train it. And to train it, we need images of the particles with corresponding positions. But now I guess you can see a catch here, right? If we have the images of the particles with the position, we don't really need a neural network, right? Means that we have already solved the problem with some other means. So that's an actual problem. And obviously it will not work if we don't have already measured the position of the particles. So what we decided to do was to use simulated data. So we simulated the particles. So here you see examples of the actual training set. These are simulations of particles. Essentially, to simulate particles is very easy because you take Bessel beams. So basically, you take Bessel functions with different combinations of Bessel functions, and you add some noise, some gradients, and you have a particle. That's how a particle looks like on a microscope. Of course, you do a lot of different combinations, and you train the neural network to recognize these particles. What's the advantage of using simulated images? First of all, we get as many as we want. Secondly, it's very cheap. Simulating doesn't cost anything almost. And finally, we know, and most importantly actually, we know exactly the position of each particle because it's the center of this Bessel beam, and since we are simulating, we know it. So we did this, we trained the neural network, worked perfectly. But now there's an obvious next question, right? We simulated the particles, and we got the neural network to work for simulated images. The question is, will it work on experimental images, right? What's the problem with that? We don't have a ground truth. We cannot really say if it's working or not. So what we decided to do was to make an experiment with an optically trapped particle. So now you see, this is a video of an experiment. This is a particle that we optically trapped, and we imaged with perfect imaging condition for tracking. It's likely the focus on purpose. Because then, when you threshold it, you get a very nice, essentially circle that you need to track, and you see that this works very, very well. And what you see here is the cross and the circle, which correspond to the standard algorithm and to deep track, worked perfectly well. So both of them give exactly the same trajectory. They agree perfectly. That's good. And one thing we can also do, we can compare not only the trajectory, but we can also compare the statistics. So we see that both of the statistics of the position of the particle correspond to Gaussians, which is exactly what we expect for an optically trapped particle, and they agree with the theoretical expectations, where they can be fit to this Gaussian, this dashed line. We can even calculate the correlation function of the particle position, which practically tells us how fast the particle is continuously falling towards the center of the trap against the Brownian motion. And we see, again, they agree perfectly, and they are both inverted exponentials fitted to this black line. Okay? So now we know something more. We know that the neural network that we trained on simulated data works also for experimental data, and that's good. The problem is that it works for experimental data that are basically perfect and for which we don't need it, right? So what we did next, what did we do next? What we did next was to basically keep the very, very same particle in the same optical trap, and we switched off the high-quality LED illumination of the microscope and place next to the microscope an incandescence lamp to illuminate the sample. Now, anyone of you who has ever touched a microscope knows that this is not a good way to illuminate a sample. So the same particle now looks like this. So this is a very bad video. It has all possible problems you can imagine. But it's exactly the same particle. So physically it's the same thing. It's just that now we are illuminating in a worst possible way. You see that there is a huge amount of noise, gain, and so on and so forth. And you see that the standard algorithm doesn't really track it well. But it looks like the neural network tracks it. You see that the circle really tracks it well. And when we compare the trajectory, we see that the standard method doesn't look right. I mean, obviously, we don't know what the trajectory should look like because it's a random process. But this gray line doesn't look like belonging to the same class of random processes of the lines that we acquired just a couple of minutes before. But the one acquired when we detected with the neural network, it looks like it's plausible. Of course, we don't really know. We don't have a ground truth. But what we can now do is to compare with the statistics. So we can compare with the probability distribution, which must be the same. And the standard method gives us something clearly wrong, spread out. But deep track gives us actually the correct probability distribution. And even more interestingly, we can compare the correlation function. So we see that the standard method produces this correlation function. And if you look at this, if you ignore these peaks for now, and you look at this correlation function, what you see is something that anyone who has taken a single course in any kind of signal processing immediately recognizes as white noise. This is a delta correlated correlation function. Well, it's a delta correlation. It's a delta function, the correlation, which means that the signal is essentially a white noise. This tells us basically that the standard method is just guessing. There is no information almost. Of course, you have these small peaks. I'm pretty sure most of you have already guessed what they are. I told you we put an incandescence lamp next to the setup. Now, since we are in Europe, we have a power grid at 50 Hertz, which means that the intensity of the incandescence lamp changes 100 times per second. Twice, because it's the square of the electric field. So that's it. This is basically only telling us we are in a country with a 50 Hertz power grid. Okay? But when we use the trace calculated with deep track, we see that it works. We get the right correlation. Now, this is very, very interesting for various reasons. I tell you two. One is that we get the right correlation function, but deep track doesn't really know anything about the fact that this is a video. It's analyzing every single image independently. This is an emergent property, which validates the tracking. And secondly, if you notice, it doesn't get swayed by the oscillations of the intensity of the light. You see that these peaks disappear basically completely. So it's not that we get more or less the right shape, but with peaks. It even corrects the gradients produced by the fact that we have a power grid at 50 Hertz. Okay, so now we were very happy. We went back to the original video, and now you see that it's actually tracking well the particles, and we could even track the bacteria and distinguish them from the particles. So now we could analyze the video. We could analyze not only this part of the video, but any part of this video as well as other videos, all with the same single trained neural network. Okay, so we were very happy at that point, and we decided that, again, this was the first example of use of deep learning in my group, so I was very impressed. This was the work that took us less time to publish. We went really from idea to submission in 2 months. So basically, I told my students this idea in end of September. We submitted the paper before Christmas. That's really a record that I will never beat. So I was very impressed, and at that point we decided we should use deep learning basically for everything. I'll give you just some examples of other work we've done with deep learning. In this case, it's a work in collaboration with a group in Spain in which they want to track active particles. So here, these active particles are rods. So basically they have like microtubules, which because of a catalytic reaction, emit bubbles of oxygen. So there is hydrogen peroxide, which gets catalyzed into oxygen and water, and propel themselves because of that. You see that they move. The problem with this is that if you use a thresholding method, it's incredibly difficult to threshold the microtubules and not the bubbles. So it's very, very difficult to actually track them in an automatic way. And of course, then you can have even larger bubbles in the background. Let's run the video again. And these larger bubbles even mess up any thresholding that you can do. So they couldn't analyze these videos. What we did in this case is to use a UNet to transform the input video into a video which had only the microtubules, so that ignored completely bubbles and all the bubbles. And by the way, this is a simulated image. So we use deep track to simulate an image. We trained the UNet on simulated images, and then we applied it to the experimental ones. And you see that this works very, very well, because it works also in these cases where you see where the microtubules is in very crowded environments in the presence of a lot of bubbles. So at this point, we managed to actually track these microtubules in all these conditions. So for example, this image becomes this. Of course, we don't do the tracking with the deep learning here. We do just the transformation of the image into something that we can very easily track. Then we do tracking with standard methods, because tracking this is trivial, just to be clear. So this was one example. I will be very, very brief now. This is another example. This is a work we did in collaboration with a group of Christoph Langhammer in Chalmers. And here, the problem was that essentially, this technique called nanofluidic scattering microscopy, invented in the group of Christoph Langhammer, permits to track very small particles, really molecules, biomolecules, when they go inside a nanochannel. So imagine a nanochannel like 100 nanometers in diameter. You have a nanoparticle go inside. Because of optical interference, you will see, like you will see in this video, a black spot. This is a destructive interference which happens because of the optics that goes on here. And if you can track this spot, then you can actually track the molecule. If you can track the molecule, you can calculate, for example, the diffusion coefficient of the molecule and so on and so forth. So you can characterize the molecule. What's the problem? The problem is that typically you want to go to smaller and smaller molecules. And when you go to very small molecules, they disappear. You don't see them anymore. But the signal is still there somehow. So what we showed here, that by using neural network, we could go at least one order of magnitude towards smaller molecules than using standard tracking methods. So that worked very, very well. And just to give you some numbers, in this work, we managed to go down to 45 kilodalton, which is like a BSA protein. Just to give some numbers, if you know what I'm speaking about. Just to give you an idea, a single base in a DNA, it's 650 Dalton. So this will be equivalent to around 100 base, well, less. Yeah, around, let's say, 80 bases DNA. With using deep learning even more extensively, now we have managed to go even one order of magnitude smaller than that, which is work that we have now in preparation. And finally, another example of this these are really examples of direct applications of the tools we developed into microscopy. Here the problem is that we want to study plankton. Plankton is extremely important. I guess you know that half of the oxygen you breathe is produced by plankton, not by plants. So we really want to understand plankton in the water. And the problem is that it's very difficult to have. There are very, very few studies that look at single plankton. There are lots of studies that look at ensembles of plankton, but single plankton is very difficult to visualize and to follow over time. What we did here is to develop a microscope, an holographic microscope, where we can have plankton and follow it for the whole life cycle. So we can look at the plankton basically from when they are born until they die or divide. So here is an example where we track a predator and a prey. And now you will see that the predator goes around and at some point will find the prey and circle it and eat it. And by the way, since this is a holographic microscope, it permits us to actually also measure the mass of the plankton and to check how much heavier the predator becomes when he eats the prey. So, you know, we can verify how much he has eaten, which is actually nice. We can also verify if a cell splits into two, how much of the mass goes into the two daughter cells. And there we, for example, notice that there is an asymmetry which biologists didn't know about because no one could ever do that. Now, here you can ask, where is the deep learning? Maybe. But the deep learning here plays a role in the fact that it's the only way we can actually make a video with this holographic microscope that lasts maybe 10 hours and analyze it in real time. So it permits us to accelerate the analysis of the holograms from taking 10 seconds per hologram to a few 50 milliseconds, which means that we can analyze this video at video rate, having a video rate of 10 frames per second. Otherwise, it will take us 3 months. So in this case, the deep learning is another aspect of deep learning where it becomes just instrumental to permit to do something that we could in principle do otherwise. Okay, so until now what I've shown you is really just applications of deep learning to microscopy that became about, but I guess all of you have noticed a trend in deep learning generally outside microscopy, and here we are really going towards I think about ChatGPT and so on. We will think of large language model. What has been the trend over the past 10, 15 years? Well, not even that, 5, 6 years. Has been essentially that when goes towards larger and deeper models, which turn out to be better. Okay? So if we look at large language model, in 2018, GPT was 100 million parameters, and then GPT-2 was 1 billion. GPT-3 was 100 billion parameters, and now GPT-4 is in the order of 1 trillion parameters. This gives you more or less a scale of how things have evolved in deep learning. Now, here, it's very important that you keep in mind that what does this mean? This means that as we use larger and larger models, we get better and better results. That's also true in microscopy. So having bigger and bigger models does return you more results. And that's also something we obviously start doing as well. Just to give you an example of this, in this work, what we did was a virtual staining. So here the problem is the following. If you go to any pathology laboratory, typically one of the things that you need to do are tissue stainings, which means that you take a tissue and you put some chemicals to highlight the different components in the tissue. Okay? So in this case, we have this tissue where we highlight in yellow the fat. These are fat cells, essentially. So they have some lipid droplets inside, highlighted in yellow, some cytoskeleton, highlighted in red, and some nuclei, highlighted in blue. But this highlighting requires a chemical staining. This means that the tissue needs to be chemically stained and observed. What's the problem with a chemical staining? Is that it takes time. It can be toxic for the cells. It's expensive. Now imagine that, for example, you are in an operating theater and you are removing a tumor. What do you need to do? You remove a part of the tumor, you send it to the pathologist, they will have to stain it, wait 20 minutes, maybe or half an hour, look at it and tell you, yes, cut a little bit more. You have a patient, surgeons and so on, just waiting in the operating room for the pathologist and the chemistry to happen. So you're really limited by physical processes. So here the idea is that you can transform this directly. You can take just bright field images of this tissue and get, through a neural network, the same staining. So here you see now the virtually stained cells. You see that the two staining are very, very similar to each other. We even quantitatively compare them, and they give the same results. And this can be done immediately. This takes less than a second with a neural network. What's the problem here? The problem here is that you need to train the neural network on huge amount of data. So you need to do a lot of experiments where you do the actual staining, you prepare your data set, then you train the neural network to do that automatically. So you see, now we have to scale the amount of data. And just to give you an idea, it's not only scaling the amount of data, it's also scaling the computer power, because the neural network somehow has to see a certain amount of data at the same time to learn, which means you need more RAM. This is the only case in which we managed to actually use the whole amount of RAM we had on our A100, and if we had that more, probably would have been even better. But we didn't have more RAM than that. So we really touched the limit of what could be done by just increasing the amount of data. Anyway, why am I telling you that? Because this is the general trend. If you want to use larger models, you need to train on more and more data, right? Now, let's go back for a second to the example of the LLMs, large language models. So, how much data do we need to train this large language model? Now, let's start with GPT-3. Well, then that was trained on 100 billion tokens. What is a token? Token, imagine, is a sentence. Okay? 100 billion. Now, when we go towards larger and larger model, we see that the number of tokens that are required keeps on increasing exponentially. So when we go to the latest models, we are really speaking of 100 trillion tokens used, 100 trillion sentences. Now, keep in mind that the population is what in the world? 10 billion. So when you go towards a quadrillion of sentences, means that you need each human to produce in the order of 1 million or 100,000 sentences. It's a lot of text in the case of large language model. And in fact, all human-generated text is more or less in that range. So you see, the amount of human-generated text is slowly growing, but there is a point, not very far into the future, maybe in a year, where all text that has been produced by human will have been used to train large language models. And we reach the point in which we use all the chemically stained images we had in a couple of hours. Because, you don't have, otherwise you have to go back to the lab and take many more data. So this applies to human-generated text by applies as well on images, images of stained tissues, obviously. But anyway, this is really a big problem. And this is the reason why, a lot of AI companies are very worried at the moment, because they reach the limit. They use everything that there is. They cannot improve their model by training more. Of course, maybe some of you are thinking, why don't we simulate the data? We could use a neural network to create new data and add that to the pool of data that we use for training. Well, let's try to do that. So this was actually tried by people. So let's say we start from a simple data set. Any of you who has done a single course in deep learning will know this data set. This is the NIST. These are handwritten digits. The task is recognizing them typically. But in this case, the task will be, let's take this digit, generate a digit automatically with a variational autoencoder or a generative adversarial network, and get a new generation of digit, and then use this digit to train a new gun. Okay? If you do that, you see that it seems to kind of work. For a few generations, we get something that, for a few generations, actually seems to work well. You see that? We can keep on training on previously machine-generated digits, only on machine-generated digits, and we keep on getting something that is meaningful. You see that? What happens after a while, in this case after about 25 generations? It happens that there is a catastrophic convergence towards the average. Because at some point a neural network generates digits that are kind of average. They are good enough. They're not perfect, but they are good enough to get a good score in the training process. So you see that you cannot really use machine-generated digits to train a neural network, because that will not work. Just to give you another example of this, you can do that also with the human faces. So this is a data set with human faces. You see that they're very diverse from each other. If you do the same as with a digit, so we create a variational autoencoder, a generative adversarial network to create a new generation of images, and then we use only this image to train the next generator, you see what happens. So this is the first generation. If you go to the second generation, you see what you get. You get essentially a convergence towards the mean. Exactly the same as with the numbers. And by the way, you might have noticed also with ChatGPT. Any of you who uses ChatGPT, you see that ChatGPT tends to converge towards the use of certain phrases and certain words. The problem is that a lot of these words go back into the internet, and then they get used to train the next large language model. So this is called sometimes AI poisoning. So we cannot really do that. So we cannot really generate images, generate simulated data to train and improve the power of our neural networks. What can we do instead? What we can do instead is to go the other way, essentially, towards smaller models. So smaller neural networks that are more task-specific and require very little data for training, because they incorporate a lot of the physics of a problem into their training or architecture. So I will give you a couple of examples of this, of work we have done recently. One is this one. Here, what we did was to essentially create a neural network that can learn to track a particle using a single image. So you take a single crop of a particle, just crop one particle, with only that, and without knowing where is the particle, it learns to track it. So you see how well it learns. In this case, you see that it's really following the particle despite the background noise changing. You can do this these are simulated images. So you see that we can do this for different shapes. It works very well. Now, of course, these are simulated images, which has the advantage that we can actually calculate how well it's doing. And in this case, we can demonstrate that it goes as well as theoretically possible, which practically means that it reaches the Kramer-Rao limit, which practically is the amount. The Kramer-Rao limit tells you how much information you can extract from a certain data set, given the amount of noise you have. We reach that. So this means you cannot do better. You can do equally well, but not better. Of course, you can retort that these are simulated data. Who really cares about simulated data? How does it work in real life? Well, then we try the same algorithm on different data sets. These are real data sets taken from the cell tracking challenge. So we didn't come up with these data sets. These are data sets that were considered by this challenge as relevant for microscopy. Here we have a data set with cells. So let's run it. With proliferating cells, these are mouse cells that are mouse stem cells that are proliferating, and you see that how the algorithm manages to recognize them. So here you see the activation map of the neural network, and you see that it manages to track them all pretty well. Now this is very impressive because we use a single cell. We took a crop of a single cell for training, and we didn't even tell the neural network you are going to track many cells. It didn't know that. It still works. And it also works with these cells, again, from the cell tracking challenge. Here it's even more interesting because the cells are very elongated, so it's really something that is not so symmetric either, but it still manages to track them. As well here, for these other cells. All of these have been trained on a single crop. And these are examples, not from the cell tracking challenge, but where we are tracking plankton. Okay, so maybe some of you are thinking, how can we teach the neural network to find the position of a particle given only one single image and without knowing where the particle is? Well, I'm not going to go into the details, I'll just give you a hint. So to train a neural network, you don't need to know the ground truth. You just need to tell the neural network when it's doing wrong. So now, if I give you an image of a particle, and I don't tell you where is the particle, you don't know where is the particle, obviously. But what you know for sure is that if you take that image and you translate it by a certain amount, the position of the particle must be translated by exactly the same amount. This is called an equivariance. And then you can use the neural network on these two translated versions of the same image and measure what it tells you, and if what it tells you is not the exact amount, the same, doesn't have the exact same translation, you know that it's not doing right. Then you have an error signal that you can use to train the neural network. It's slightly more complex than that because you cannot use only translation, you have to use also rotations, but you can use it. And that works very well. And you can also use other equivariance. The equivariance doesn't need to be only position. This we have shown that it works, for example, in holography, for Z position, for the mass of an object. So, as long as you find an equivariance, you can exploit it to train a neural network with this symmetry. And this reduces dramatically the amount of training that you require and the amount of data. Data, in this case, single crop, training, this can be trained in 5 minutes on a CPU. So take your laptop, CPU, 5 minutes, you get it to work. Another example of using essentially geometric thinking in order to improve neural network. I'm not going to go through the details, but another problem that you have when you do microscopy with cells is that once you have detected the cells in each frame, you need to link them across frames to get trajectories. Like if you want to repeat Perrin's experiment, you will have to do that in order to then calculate the mean square displacement and verify diffusion. Well, what we show here is that this can be done very, very efficiently and very, very correctly using a graph neural network. I'm not going to go into the details, but the advantages of the graph neural network are multiple. And first of all, it does it better than other methods, like the classical Hungarian algorithm. But more importantly, it permits to extract interesting properties about the trajectories, also in cases where it's impossible to reconstruct the trajectories. Now you can ask, when is it impossible to reconstruct the trajectories? Well, for example, if there are objects that are blinking. Sometimes they go dark, you don't know where they are. Or if you have a system that is very crowded and you have a low frame rate, so you don't know which particle is which frame to frame. These cases are not analyzable with standard method, basically, but the graph neural network can still analyze them. And again, this can be trained on very, very small amount of data and in a very, very efficient way. Because it turns out it actually has a very good capability of transferring the learning from one problem to another. So you can train on a data set and apply a completely different data set and it works. The reason is because we transform the input into a graph, which is a very high-level representation of the problem. Anyway, these are two examples of this direction where I think the field is now going and should go, which is towards models that are really focused on solving one problem and solve it in such a way that they really exploit the properties of the problem to simplify both their training and their time for execution, which also means, by the way, that they will require less energy to train and to be executed, which is a big concern in terms of, well, ecological concern in the use of deep learning. Okay, and finally, very, very quickly, I would like to, let's say, advertise the tools we have developed in the process. So essentially, in developing these tools, we developed this software tool, which is DeepTrack. This is a Python package. So for the ones of you who use Python, you can install it with the pip install DeepTrack. And this is a tool that now permits to create simulation pipelines for microscopy, which can then be used for training neural networks. And it's available on GitHub, open access, and is now becoming really fully documented with examples that are runnable. You can run them immediately on Colab. Over the next 2 months, we will have everything ready. It's mostly ready already, but we are just polishing all the last details. If you want to know why we are doing that, it's because when we started in 2019, the standard framework for deep learning was TensorFlow. So we went with TensorFlow and Keras, but then TensorFlow basically stopped getting support from Google a few years ago, so it's shutting down mostly. And now everything is moving to PyTorch. So up to version 1 of DeepTrack 2, we were basically using TensorFlow, but now the new version 2, is basically all oriented towards PyTorch. So there's been this transition, so what we are doing now is to translating essentially all the examples and ensuring that they work in PyTorch as well. And another thing that happened is that up to DeepTrack 2.1, DeepTrack 2 contained also the neural networks we were using, like Lodestar, Magic, and so on. But when we decided to do this switch to PyTorch, we also decided that we should span out the neural network part of the software, because many people wanted to use it outside microscopy, and we kept on receiving questions like, I would like to use the neural network, but I don't do microscopy, can I do it? The answer is, of course, yes, but it was not that clear. So we decided to span out this part into dplay, which is another Python package, which you can install with the pip install dplay. And this if you wish to, for the ones that know about it, this would be more or less a Keras Lite that works on top of PyTorch and permits to configure in a very efficient way PyTorch models. You get a PyTorch model at the output, just if you're asking. But yes, things like history, fit methods, and so on, which are not available in PyTorch or in Lightning. So it builds on top of that. Again, it's open access and fully documented. And finally, yeah. That's how much time do I have? 1 minute? Okay, finally, 1 minute, more advertisement. So, okay, these are all the various methods that are incorporated into DeepTrack and dplay. And there are these new methods, Miro and Gaudi, that are going to come up. Well, Miro is actually in archive. Gaudi will be in archive probably in a week or two. Miro is for particle single molecule localization clustering. So if you do that, probably you want to have a look at that. And Gaudi will be for basically understanding the underlying physics in complex phenomena using graphs, and will come out in a month or so. Okay, but that said, a few years ago they asked us to organize some PhD courses on deep learning for microscopy. At the beginning we did this in ETH because they asked us, and then many other people asked us over the years, so we organized these courses. Now, it might be interesting for maybe the PhD to know that we organize this course now, I think yearly, in Gothenburg. So if you're interested in taking a PhD course on deep learning that uses these tools is being, and it will not be taught by me, it will be taught by Daniel Mitvet this year. He starts next week for this year. And all this knowledge we accumulated in the courses then went into a book, which is called Deep Learning Crash Course, which is published by No Starch Press in San Francisco. The book comes out officially in the summer, I guess, but it's already available in early access. This means that since last week, the full draft is available, which is basically correct. It's not polished. It's not polished means that it doesn't, the final proofreading. There is not the index, these kind of things, but there is everything else. And this is a very nice course because essentially we start from no knowledge of deep learning. So we don't assume any knowledge. You need to know how to program, possibly in Python, NumPy, Matplotlib. But from there, we take the reader up to the most advanced techniques, including GANs, diffusion models. One of the examples we make is, for example, diffusion models for super resolution microscopy, which we also independently published just a couple of weeks ago. So it's really something that takes you from zero knowledge of deep learning up to the state of the art, and all hands-on. And this is the preliminary cover, so it's only my name, but this is a collective work of 4 of my students plus 2 of my collaborators and myself. Okay, so that gives you more or less an overview. So I tried to give you, first of all, an example, very worked out, about trying to give you a feeling for what convinced at least me that we should use deep learning extensively. Then I gave you a very quick overview of the trajectory of how deep learning has been used in microscopy, especially in my group, but also trying to give you a feeling for where I think the field should move in the next years. And finally, I advertise you some tools we have produced both to do microscopy, deep learning, and to learn deep learning. And with that, I would like to thank you, and obviously, I will take questions.
Okay, it's time for questions now. If you can add any questions, are there any questions? So, while people coming up with questions, maybe I could ask you a question. Just a seemingly unrelated problem that we face in some of our branch of research. We are looking at highly disordered configurations of forces, which are like point-like particles, and there could be the disorder could come from either intrinsic disorder at pinning centers or from interaction forces. So, like, one can train these things by, one can principally simulate this kind of thing. Could this machine learning methods be helpful to kind of reconstruct, like if you have like a set of disordered snapshots from experiments and you want to extract the information, how much it is coming
actually,
from?
Actually, this two answers.
Yeah.
The first, this reminds me vaguely of glass dynamics, maybe, or not?
Yeah, it can
because
involve,
if it does,
can involve glass dynamics.
Because
also.
if it does, there is a paper in which I'm co-author, which is kind of a review, but it's not really a review. In Nature, just came out last 2 weeks ago. What is Nature Review Physics? In which it's a big group of people and just one of the co-authors, but it speaks about how machine learning can be applied to glass dynamics, and he has also several benchmarks and idea how to do that. So maybe it's worth looking into that. But the other thing that might be very interesting, we mentioned that there as well, is that, and we are also doing that for colloidal particles, is to study how to use graph neural networks, like magic kind of approach, because they can learn to recognize interactions between the nodes in the graph, which would be in your case the vortices, And then the question can be posed as, can they learn to recognize interactions or not? If they learn the interactions, means that they are useful for predicting the behavior of the system. If they don't learn any interaction, probably the system is independent. So that's one way.
Yeah, so maybe just a very quick follow-up question. If you take, let's say, polydisperse colloids, which are glass formers, right? So could you say something that is it helpful, like your techniques in trying to understand?
Yeah. And as I said, there is just this review, not tutorial, but more perspective, just 2 weeks ago out. So I'm not an expert in glass dynamics, just to be clear. So there are really the real experts and just one of the contributors there. And I think they really know much better than me how to do that in glasses. So it's worth having a look if you're really interested in that. I know very little about that.
Oh, good, great. Yeah. Then if you can say loudly, or you can give a microphone. Yeah,
I can speak loudly. Very nice presentation, thank you. You mentioned at some point about one example of a particle very small comparable to BSA you mentioned specifically. We work also with BSA, and I was impressed that you can track this. Do these methods basically help you lower the detection limit, like go smaller and smaller to protein size, like be able to detect proteins with the microscope?
Okay, so the question is about what limit we can reach first of all, and then what is the reason why we reach that limit. So here, 2 things. First thing is that this is done in a nanochannel, so this technique called nanofield scattering microscopy is really, the idea is really the fact that they are in a nanochannel. This produces some interference in the light which permit to alight the particle. So that's critical. Without that, you will not see anything. What the learning can do, and now we can do down to insulin, so few kilodalton. Since you know, I didn't know what Dalton were when I started this work, just to be clear. That's why I explained this. So Dalton turns out is 1 nucleon equivalent. But I understood that during this work. I'm not a chemist. But anyway, so now we can actually detect something the size of insulin. What's the trick? The trick is that we can lower the detection limit, but here, at some point, it becomes important the difference between detection and positioning. We don't see the molecule. I wouldn't be able to tell you where is the molecule when I go down to that limit, but I can tell you there is. Because you don't see it anymore, and the algorithm cannot track it. But I can detect its presence from the signal which is hidden in the noise. So yes, it lowers the detection limit, and it lowers also the positioning limit up to a certain point, but we can detect also below the limit in which we can recognize what the particle is. This part is not published. We are wrapping it up in these days, basically.
Okay, I just use my. Yeah, in one of the page you talk about load start and checking things in one single images, right? Can you go to the presentation? Yeah, this one. So I just wonder, because I just want to confirm with you, so the real image is the first one, right? The rest is a different shape, is you generate or simulate. Is it correct?
So the question is which ones are real images?
Yes.
So the top row are all simulated images. These ones are all real images.
Yeah, okay. My question is like
so
this.
And these 3 are from the self-tracking challenge. These are videos we acquired in our work with Plankton.
Yeah, I get it. My question is like this, is because in previous you talk about the AI, if you just use their generated data, they can poison itself because it's not matches the physics and anything. So I just wonder, for example, this moon-shaped things, is it realistic in actual real life or something like that?
So the question is whether this will be realistic?
Yeah.
Maybe, I don't know. But here we wanted to basically, essentially what we did here is to test different shapes to see where was the limit. Why it's interesting for us to have, so just to be clear, these 3 shapes are very symmetric.
Yes.
This is a bit less symmetric because it has 2 axes of symmetry, but it still has a very well-defined center.
Yes.
This one, it's not clear what is the position it should track. There is not a clear center. So we wanted to check if it will learn to track a consistent position over the video, and it does. So it's interesting. These 5 videos are more to test the method and understand its limit.
Okay.
And that's why it's done also on simulated data, because we want to be able to actually say something about the Kramer-Rao limit. And this one is really, for us, interesting because it permits us to understand how the algorithm understands shapes that are not very highly symmetrical. Since we are using symmetries in the training process, we wanted to understand if it was just collapsing into recognizing symmetries, or it was really doing something more than that.
Okay, my last question is like this, is because you talk about, I don't know whether it's possibilities, it's something like you misguide these systems because you will generate something not realistic, because this data also you say is simulated, right? So do you consider these possibilities?
I don't understand the question.
I mean, is there any risk of misguiding these systems to generate the data unrealistic?
I mean, the point is that these examples here are independent from these ones. So each one of these videos is trained on one image of that video. It's not that we didn't use a single image to train all of this. So in this video you will have to crop one of these cells and train on that cell. So this is not seen in training this video at all. And when I train for this video, I will have to take one crop of a cell from this video.
Okay, thank you.
So it's really, but the point is that we can train this model in 5 minutes on CPU. So it's really not a big cost to train for each video. It would be very different if you had to train something like the size of ChatGPT of 4, because then you need 6 months on a super computer cluster. Then it's not viable. But 5 minutes or less on a CPU.
Thank you.
It's probably less than the net energy cost of running the video. Just to give you an idea.
In all the applications or many of the applications that you suggest here, you actually suggest that the artificial intelligence can actually improve microscopy, improve detection of particles, improve maybe resolution of something like microscopy or something like that. How easy is it to prove that what you actually improve or to get this information is still there and not just fake?
So basically the question is, how do you know that you are not making up information? That's always a problem with any deep learning approach. But the advantage with microscopy is that you can actually see the data. So it's very easy to validate, in a sense. But for each problem, you need to validate it. In the sense, obviously, you need to check. So in this problem, that's why we rely on the cell tracking challenge. So we have a ground truth made not by us, but made by someone else. And there are all the algorithms that have run on the cell tracking challenge against which we can compare our performance.
So if you check it, do you see a usual method, for instance, that you make the images worse first and then test it, have an equal set of data where you can have full information? How is it that you usually
if I understand correctly, the question is about how do we test if it's working and if it's not making up data. Or this is very specific for each problem, in my opinion. You cannot test generally. So for each problem, you have to think how you do that. It requires effort. That's why I don't really believe in the, dooms.
So it's rather
a human needs to think about how to validate that the AI is doing the right thing.
So you see the application rather in speed up analysis than
It really depends case by case. Sometimes it permits to speed up the analysis, other times permits to be more precise, like here. In other cases, it permits to see something that, or detect something that it would not be possible, like in the NSM. In other cases, it permits to do analysis of data that would not be possible otherwise, like in MAGIC, because if I want to trace, typically no one really cares about the trajectory of particles in colloids. Typically you care about the diffusivity of the particles, because it permits you to tell you something about the size. So if I can get the diffusivity by passing completely the reconstruction of the trajectory, that should be fine. That's an example where it becomes obvious, but you cannot really do that in any obvious way with standard methods. You might come up with one. I'm not saying it's impossible, but it's not straightforward. While with MAGIC, it's straightforward. You train to predict the global diffusivity, and in a sense, I guess it will predict in a probabilistic way which particle can be connected with it. I don't know what it does inside, we don't need to care. But then, of course, we will have to validate it. How do we validate it? Well, one way would be, I have a video with very high frequency, where I can really reconstruct the trajectory and calculate the diffusivity, but then I feed to the neural network sampled down versions of this video where one frame maybe 100, and see if it can still give me the right answer. But it's very specific. That's, I think, where human creativity still has a huge place. An example, actually some radiologists told me that people in radiology were already saying 20 years ago that radiologists would not have a job because machine learning at the time would come and take their jobs. And what he told me is that this didn't happen. What happened is that a lot of tools are now used in radiology, but even more radiologists are needed to check that the tools actually do the right thing. So that's more or less a pattern that has been happening in all AI. One other thing that people typically don't remember or don't notice is that most of the money that goes into AI nowadays doesn't go into the infrastructure or the algorithms. It goes in human annotations. More than half of the budget of OpenAI goes in human annotations and in humans interacting with the chatbot to get their reinforcement learning to improve them. So really, the cost of AI is really related, is intrinsically connected with the humans checking the quality of what comes out of the AI still. So the good thing of going to smaller, more focused models that exploit symmetries in the problem is that you guarantee something. Like, let's say you want to make a simulation of something. If you enforce at the level of algorithmic training that energy must be conserved, you don't need to check it. Of course, you can also make train an algorithm that doesn't have this as an internal rule, then you will have to learn it, which means that you make the training much more expensive, you have to check much more carefully and so on. I mean, but it's a very good point, and there is not a simple answer.
Okay, I had a question which relates to question 4 questions back, which I thought was very fascinating. That you can find that there is a particle in a place, but you can't see where it is. Can you, with this specific example, comment on all the other questions? So, how do you know that there actually is a particle there if you cannot see where it is? What do you train against? And are you using deep learning, or are you using some physical insight? You're talking about that. You mentioned that you can see it from the noise, but which patterns in the noise is it that you actually exploit? Do you know that?
Yeah. Okay. No, but it's
whatever you want to like to say.
Yeah, sure.
It's unpublished. I understand. So
no. It's not that it's unpublished. It's not very secret. In the sense, if you take this example, so obviously when we have very large particles, we have a very high signal to noise level, like this one. So you can see the particle. Let's go back so that you see. This is a very large particle. Just to give you an idea, this is not a BSA. This is 300 kilodalton. It's 10 times bigger than a BSA. That's why you see it so clearly. And here it's very tiny. So what happens? I guess your question is how we get the physics into the system so that it can recognize the presence of a particle even when it looks like there is no clear signature of the particle.
Yes.
I can answer in 2 ways. And I will answer first in the way I will explain it to physicists. Think about Fourier transforms. If I have a signal, a small sinusoidal signal and a lot of noise, you don't see it in real space, right? But if you make a Fourier transform, you will see a peak and everyone will recognize it. So maybe there are transformations of this signal where this becomes obvious, which we don't know exactly what they are, but the neural network will learn to find them out. So that's how I understand it. And then the question, which it will be more the answer for someone working in machine learning, is how do you get the neural network to find out these transformations? Well, you take a neural network, you start feeding with simulated data, because we can simulate this system very well. It's a physics, we simulate the optics. We simulate the system so we know exactly how it looks like and how it should be. And what you do is to train a neural network with large particles. So it learns to recognize the large particles. And then you start making the particles smaller and smaller over time, so that the neural network learns to recognize smaller and smaller particles. It's like when you train anyone. You start from the simple task. Once it learns the task, you go to more difficult ones. And at some point, turns out, you can go beyond the point in which you can recognize by eyes the particle, and below that point. Of course, now you can ask, how do you know that it's actually recognizing the particle and not giving you random responses? Well, we can check, because we can ask the neural network is not predicting yes or no. The neural network is giving us the weight of the particle, the kilodalton essentially. So if you make a channel and we put insulin, we want to get 6.2, I think, don't remember exactly the number, kilodalton. So if the neural network tells us there is a particle, but it's 10 kilodalton, and we know it's not right. And if then even simpler example, if we give a channel with nothing, just buffer, we want it to give us an answer that there is nothing. So that's how we check.
Do you think that somebody can train their own neural network in their own head to actually see this also? I mean, a very skilled microscopist maybe can see this.
You're asking whether, okay, for everyone. The question is whether, like we can train the neural network, can we train our neural networks in our brain to recognize? Sure, that's what you do every day. Learn a new language, what are you doing? I mean, this is really how the brain works. You have the amount of signal think about when you are in a crowd and you listen to a single person. It's not that you're here and don't hear everything else. Your neural networks are doing a very good job of cancelling the noise from everyone else. When you cannot do this well, then you can have serious problems. Autism, for example, is really a syndrome where you are not able to filter out very well signals. So this mechanism in your brain is not working very well, you get overwhelmed by information. Now that I'm listening to you, someone speaks, I will probably not notice that. But I'm not saying that you will be able to train yourself to do this task specifically, because you cannot probably do Fourier transforms in your brain very efficiently. But maybe to some degree, yes.
Great, we had many questions today. Let's thank speaker again.